Hello, welcome back. The title of this lesson is called The Meaning of the Equations of Motion with Constant Acceleration. So this is probably one of the most important lessons in all of physics because it introduces you to some of the absolute core equations that we use in the beginning part of any physics course. All right. Now what we want to do in this lesson is just to get you kind of warmed up to these equations because they look intimidating, but I'm going to break down that intimidation. I'm going to show you how easy they are to understand. And then what we're going to do in this lesson is mainly break it down to understand why they are what they are. We're not going to derive them in this lesson. I'm not going to prove it to you that they're correct. I just want to write them down so that you get familiar with them, and let's analyze them and make sure that they make sense. Then in the next lesson, once we know what they are and we know that they make sense, in the next lesson we will derive them. We will derive them from a blank sheet of paper, and you will derive every one of these equations to know what they are and where they come from. And then after that, we'll use them to solve a ton of problems to get practice, okay? So here are the equations of motion. Here, I have a column here with the equation that's listed, and I have a column here with the missing quantity. Now, before we talk about anything, I need to make it absolutely clear that these equations of motion are when we have constant acceleration. I'll say it again. We have to have constant acceleration to use these equations, okay? So if I'm in my car and I'm accelerating at a constant rate, I can use these equations. But if my foot is on the pedal and I'm going back and forth, back and forth, back and forth, and I'm just jerking it around, then it's not going to be constant acceleration. You can't use these equations, right? And we'll understand after we derive them why you can only use them for when they're in constant acceleration. It has to do with calculus and a constant we can pull out of the integrals. So that's why acceleration has to be constant. But the good news is that these equations, we're going to be using them in the x direction first, horizontal motion. All right, you can see the x's that are running around in here. And you can see the a for acceleration. That's acceleration in the x direction. But then we're going to start to talk about vertical dropping, and we're going to use the exact same equations. We'll just turn the x's into y's, and we'll turn this acceleration A into gravitational acceleration. And gravitational acceleration is very, very close to being constant near the surface of the Earth. So we can use these equations, very slightly modified, to model how things fall. Then we can talk about how things move in a curved path, also using these equations. So they have very practical value, okay? Now, in a rocket ship, when things are not constant, then you have to use more complicated calculus to solve them. But these definitely have their uses. So the very first thing I want to say before I do anything else is the following. We have 1, 2, 3, 4, 5 equations of motion, but some textbooks don't list them all. And the reason they don't list them all is because of the very, very important fact that these two equations, the very first two in my list right here, these are what I call the core equations, or the fundamental. Fundamental, if I can fit fundamental in here, right? They're fundamental. In other words, these first two equations, they come from first principles. They come from basic calculus, okay? The remaining of these equations, right, they come from these up here. So basically, I have a bunch of equations on the board, but actually these two at the top are way more important, okay? To be 100% honest with you, I don't often use the other equations of motion. I mean, I do sometimes. It really depends on the problem. Sometimes the problem really lends itself to using one of these other equations. But you don't have to use them because honestly, these first two are really all that you need. Now, what do I mean when I say that these come from these? What I'm saying is in the next lesson, what we're going to do is we're going to derive these two equations from calculus, and then I'm going to show you how to take these two equations and turn them into these three. So these different types of equations are just different flavors of these, right? And before I go any further, I have to erase this because this little red line, I'm just going to put fund. It's just bugging me. All right, I don't want to have the board cluttered here, right? So these are the core fundamental equations, and these equations come from this. So I have a column here called missing quantity. So basically there's several variables that we use when we talk about how to describe something's motion. We have the x variable, which is its position along the x-axis. Because remember, this is only for one-dimensional motion along the x-axis, same as before, right? So we have the x. But then you see this thing called x with a sub-0, which means x naught. The way you say this is x naught, the way you say this is v naught. When you see a 0 there, it means initial value. So this is its current position after the motion has happened. This is the initial position. If you start the initial motion, the initial position at 0 on your coordinate system, then x0 is just 0. So this is the initial position, and this is the final position. You can think of it that way. When you see x minus x0 together, that's delta x. That's how far the thing moved. It's x is the final position, x0 is the initial, x minus x0, that's just how far it moved. Delta x is another way you might see that in other books, okay? So we have x, that's because we're talking about motion along x. We have a. Now in some books you'll see a with a little x after it because this is the acceleration in the x direction. I don't need to put a sub x. You know that this is motion in the x direction, so the acceleration is in the x direction that we're talking about here. So a is its acceleration. T is for time. There's nothing special about that. T is the number of seconds after the experiment starts. And then we have v and v0. V is the final velocity of the motion after some time has elapsed. And what do you think v0 is? It's the initial value of the motion. So basically, you always have a situation where the experiment starts, and that's when time is 0. So when time is 0, at 0 seconds, you have an initial position x sub 0 called x0, and you have an initial velocity v sub 0, which we call v0. So that's why it's x0 and v0, because those are the position and the velocity when time is 0. That's why they put a little 0 there. In some books, you might see an I for initial, but really, usually you see x0 and v0. So these are the initial positions. Then you have some time that has elapsed, and then the particle is somewhere else, some other position, and traveling with some other velocity. So after some time has elapsed, it is at some new position, x, which is the final position. X is running around all these equations. And it's traveling with some velocity v, which you also see running around these equations. So x is the final position, v is the final velocity. So I think we've covered them all. Basically, you have time. And when time is 0, you have initial position, x0, and initial velocity, v0. So those are all the initial conditions when time is 0. That's why they're in these equations, right? And then after that, what you have is some time elapses into the future. And then after the motion of the particle happens, at some future time, t is equal to something in the future, you have a new position and a new velocity. Those are just x, the new position, and the new velocity v. And then of course a is running around here because if the thing is accelerating, then you have of course the acceleration that's happening causing the thing to speed up or slow down, right? And it's the acceleration in the x direction, of course, because these are only equations for the horizontal or the x direction, right? Last thing is a here is always a constant for these equations. In other words, a is going to be 3 meters per second squared, or a will be -2 if it's slowing down, meters per second squared, or a will be 0. A will never be changing with time because these are equations of motion with constant acceleration. So anytime you see a, it's always a constant. A can be 0, 0 is a constant, 1's a constant, but a cannot change during the motion. When you drop something, later we're going to use these equations, we're going to turn them on their side, and we're going to make a equal to the acceleration of gravity. Acceleration of gravity is very close to constant near the Earth's surface. We call it g for gravity. So these equations will be used then, and acceleration of gravity is also a constant. So we're doing the same thing in both cases. All right, so we have a column here called missing quantity. So in this variable, in this equation, we have v, v0, a, and t, but we don't have any x's. We don't have x minus x0. That's the displacement, delta x, that the thing has traveled. That's not present in this equation. In this equation, we have all of these variables, but we don't have any final velocities. We don't have the final velocity there. We don't have any time at all in this equation. We don't have any acceleration a at all in this equation, and we don't have any v0 at all in this equation. So the missing quantity is helpful if you have a problem that doesn't give you any information. Like if I have a motion problem and I don't actually know anything about how long it takes the motion to happen, I don't know what the time value is, then I might be drawn to using this equation because there is no t in this equation. Or if I don't know what the acceleration is, I might go and use this one because this one has no a in there. Now, you don't have to do that, but that's why I put the column here. That's why it's useful to know some of these equations have missing variables because we have derived that, we've combined them in such a way to eliminate those variables. And so depending on your problem, you may want to use one of these. But keep in mind that these last three they come from these. You can solve all the problems with these. You may have to eliminate variables, you may have to substitute in or something, but you can get all of these from these two. So before we go on, what I want to do is give you a prototype in your mind of what constant acceleration actually means. And I've done this before, but I want to do it here because it's very, very important to keep in mind. So let's, before we talk about these equations anymore, let's draw a little prototype in our mind of what constant acceleration really looks like. All right, so this is the time in seconds. This is the time in seconds. This is the time in seconds. And up here, this is going to be the position as a function of time. This is the velocity as a function of time. This is the acceleration as a function of time. All right, so what we basically know, let's just say that it's constant acceleration. Constant acceleration, what does it mean? It means as time goes on, the acceleration never changes, so it has to be a flat line. It doesn't go up, it doesn't go down, it doesn't shake all about, it just stays flat. It can be a positive number, it can be a negative number, in which case it would be down below the axis flat. Or it could be 0, which would mean there's no acceleration at all, it would be here. But it has to stay constant for these problems. It cannot go up and down. If it does change, where you have in one part of the problem positive acceleration and another part of the problem negative acceleration, then you need to break your problem up into two problems, because these equations can only be used when A is constant. But if you have a constant and another constant, and there's some change in the middle, if you split your problem in half and deal with half and then half using the different values of acceleration, that's okay. But when using those equations, A has to be constant. Now, if we have an acceleration that is constant, what does it mean? It means every second that goes by, I'm gaining the same amount of velocity, because the units here are meters per second squared, meters per second. So every second that goes by, I'm gaining the same amount of velocity, the same amount every second. So that means the velocity curve is actually going to look like a straight line with some slope to it, like this, right? And the units of velocity are meters per second, of course. And this is because in the first second, I've picked up some speed, and then the next second I gain the same amount, and the next second I gain the same amount, and the next second I gain the same amount, and so on. So my velocity is going up in a straight line. I drew this thing in a very slight curve, forgive me. It's supposed to be exactly a straight line, okay? And then what does it look like in our motion, in our position, which is a unit of meters, if the velocity is moving like this, or if the velocity is always increasing? That means in the beginning, I have a velocity of 0, and I'm not moving very far. But then toward the end of the motion, I'm moving extremely fast. It cannot be a straight line because my speed has changed the whole time. In the beginning, very, very slowly moving, but at the end, really, really, really fast. So what this looks like in terms of motion is a parabola that goes up like this, right? So when you have velocity always changing, at the end of the motion, you're moving incredibly fast, so you're covering a lot of distance in a short amount of time. But in the beginning, your velocity is slow, so you're not covering much distance in the same amount of time. In a 1 second window, you don't cover much distance. In a 1 second window, you cover a lot more distance up here. All right, so the prototype motion for position, x of t, I mean, I'm just giving you an example. It can be anything, but the prototype, since this is a parabola, would be that x of t is t squared. Right? So the position might be a function of time where time is squared. Remember, this is the time axis, this is x, and so this is exactly a parabola, of course, cut off here at the origin. And so this could be a motion that would look like this. Of course, it doesn't have to be t squared. It could be some, 4t squared plus 2t minus 3. It just has to be a quadratic like this, right? And then we already learned that if we have the position function, we can get the velocity, right? We already know that the velocity is the derivative of the position, right? Which is the derivative of whatever the position is, d dt, the derivative of t squared, because x is equal to t squared. So I'm just going to put it in here and take the derivative. So the velocity of this thing right here, the derivative of it, take the 2, bring it down, and then t to the first power. So the velocity is 2 times t, right? 2 times t. And notice that this is a line with a slope of 2 and a y-intercept of 0. Y-intercept of 0, some slope, and it's a line. So this equation that we get by taking the derivative of the position function, when the position function is a parabola, gives us a line which gives us exactly what we just graphed a second ago. And then we also know the following. You can already guess where we're going with this. And we know that the acceleration is dv dt, the derivative of the velocity with respect to time, which we can take the time derivative of. We just plug in the velocity, which we can just put in 2t right there. And we can take the derivative of this. What is the derivative of 2 times t? Well, there's an exponent of 1, so it comes down, and you get 2t to the 0, which is 1, so you get an acceleration of 2. This is constant acceleration, which is exactly what we graphed, something that's a constant like this. All right, so I'm going to circle this. I'm going to circle this. I'm going to circle this. I just want you to have these prototypes in your head. When you're thinking about velocity and position and acceleration, when the acceleration is constant, think of the following. Okay, this means that the position function is something like a quadratic. Doesn't have to be this exact one, but something like it. When you take its derivative, you get a line. So the velocity is a line. It has some slope. Doesn't have to be this one, depending on what we start with, but it's going to be some kind of line. That's what we get here. And then when we take the derivative of that, it gives me a constant. This is what I mean by constant acceleration. This is the situation in which we can use these equations of motion. When the acceleration is constant, it implies a velocity that's increasing linearly with time, which implies that a position is increasing with some sort of quadratic nature. So let's look at this. What we're saying is that when the acceleration is constant, the velocity is some kind of line. Some kind of line. The velocity, these are the core equations, is some kind of line. Because v naught is a number. It's the initial velocity. So v is equal to mx plus b. I just flipped it around, right? This is the slope, this is time, and this is the y-intercept, or the y-intercept, the initial velocity. And so in our example, we said that it was 2 times time with a y-intercept of 0. We started off with no velocity at all, and we can see that this is a line, exactly as we predicted over there. And then we said, when this happens, we expect to have some position function that is quadratic in nature, quadratic in time. And I gave a simple one here, but quadratic in time. Here, this is the position. Don't worry about the x naught. That could just be 0, but you can see that you have a quadratic function in time. Now you have an extra term here. We're going to talk about that in a minute, but it's still a quadratic in time. 1/2 times a is a number times time, squared. And then you have a number times time. So remember I told you, you just need to have, for constant acceleration, the position function will be some kind of quadratic in time. It could be 3x squared plus 2x plus 5. That's still a quadratic that's going to make that shape. And I'm showing you, we start over here, we say what happens if acceleration is constant, we predict a linear velocity, and we predict a quadratic in time for the position. And then we give a prototype example for you to recognize that taking these derivatives does give this. And then we go back to the equations of motion and say, aha, this is a line, and this is a quadratic function. So it matches with what we expect. Now, before we talk any more about the equations of motion, let's just see if this actually makes any sense, right? Let's just see. We know that v is equal to v naught plus the acceleration times the time. I'm just going to write this guy down. So let's then take the derivative of this thing. Let's take the derivative of both sides. So what we do is we say that dv dt is equal to what? We're going to take the derivative of this, but this is a constant. It doesn't change. It's just the initial velocity. So you get a 0 here. What's the derivative of this? This is a number. It's just a number like 5 times t. So its derivative is just going to be the number out in front, a. You know, the 1 times the a, and then the exponent goes down. So what do you get is dv dt is just equal to the acceleration, which is a constant. So what we figured out is that when we take the velocity function that we're saying is correct for the equations of motion, when we take its derivative, we get an acceleration which is a constant. I've been telling you this has to be constant the whole time. That's the same thing we got here when we dealt with a concrete example. Now let's do the same thing over here. Let's take this equation. Let's take this equation, which is this one. X minus x naught is equal to v naught t plus 1/2 a times t squared. Now for this, usually you write the x naught over here, because this x minus x naught, it means delta x. It means how far have I moved beyond my initial position. But for this, let me move it over here. So what we'll do is we'll say x naught plus v naught t plus 1/2 a times t squared. I'm just going to move it to the other side, and now I have the final position. Let's take the derivative of x with dt, and let's see what we get. What's the derivative of a constant? This is just the initial position constant, it's 0. What's the derivative of this with respect to time? This is a constant times time, so the derivative of that is just the constant that sits out in front. Time disappears. 1 times this gives me this, and then the time has a 0 exponent, so it disappears. Now what's the derivative of this term over here? The 2 gets multiplied, so it's 2 times a half, and then we have times the a, and then the t to the first power. All we did was multiply down by 2, and then the exponent here gets reduced by 1. So dx dt is going to be equal to v naught, and then we have a 1 times 1 here, and then times a, and then times t. So all we have is a times t. So what did we figure out here? We figured out that dx dt, which we know to be the velocity, so I could just say v is equal to v naught plus the acceleration times the time. Look at this equation. This is exactly what the other equation of motion is. All I'm doing here is telling you, hey, I'm giving you these equations of motion. I haven't proved them to you yet. I haven't shown you and convinced you they're true. But you're going to have to trust me that they are correct, okay, when the acceleration is constant. And I said these are the fundamental ones. So really, if this does tell me the velocity in the future, if I take its derivative, I should get the acceleration. So if I do this and I take its derivative, what do I get? The acceleration, which is exactly correct. And if this equation is its position as a function of time, when I take its derivative, I should get the velocity of the particle. So I write it down, move this over, take its derivative, and I figured out that dx dt is the final velocity, and it's v naught plus at. But this is v is equal to v naught plus at. This is the other equation of motion. So what I figured out is that when I take the derivative of this equation, derivative of position, I get this, which is the velocity. And when I take the derivative of this one, the derivative of the velocity, I get a constant acceleration. So I'm just showing you, I'm not proving it to you, but I'm showing you that it's self-consistent, because you know that you should be able to take the derivative of the position and get the velocity. We did that because we have the equations and we verified it's true. And we take the derivative of the velocity and we get the acceleration, which is a constant, which we have again done, and it's true. So we're almost done. But believe it or not, we haven't hit the main thrust of what I want to teach you in this lesson. What I want to do is I want to ignore these equations for now. I want to focus on the important ones. And I want to talk physically about what they actually mean. So we know that they're true, or that we suspect they're true based on what we said. I want to write them down. On this board over here, I'm going to write down the first one. V is equal to v naught plus the acceleration times the time. And on the next board, I'm going to write down the other one, which is the other fundamental one. X minus x naught is equal to v naught t plus 1/2 times a times t squared. So these are the two equations which I'm claiming are fundamental or core. I'm going to show why they're core later. These other ones just come from these. They're just different ways of rewriting these over here. All right, so what does this actually mean? All right, when we have a situation, we're saying the final velocity of some particle is equal to its initial velocity, wherever it started, plus some acceleration times some time. So if I draw a quick little graph over here, this is time in seconds, and this is the velocity. And what if I start out with some initial velocity and I end up at some final velocity? Basically, all particles are going to start off with some initial velocity and they're going to end up at some final velocity over some time period. That's what acceleration is. It means you change the velocity of the thing over some interval, right? So if you start off with some velocity and you're accelerating in a constant way, then you should have a line that goes up to essentially to the final velocity kind of like place right here, essentially. And this time interval is what we call t. Notice that this is just a line of increasing velocity, which is what we already said we had. We've said that with constant acceleration, we should expect the velocity to go up in terms of a line. The only difference is now we're starting, instead from 0, we're starting at some initial velocity. In other words, maybe the problem is a baseball starts with an initial velocity of 2 meters per second, and then it accelerates with some acceleration of 10 meters per second squared. Find the blah, 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 blah. Well, the initial velocity when the clock started was some number. That's v naught. And then as acceleration happens, it ends up in some final velocity over some time period. How much velocity was gained? How much velocity was gained here? What this is equal to, the difference from the initial to the final velocity, is the acceleration that was happening multiplied by the number of seconds. right? Because what is the unit of acceleration? Meters per second squared. Meters per second. So every second that ticks by, I gain that much more speed, that much more speed, that much more speed. Whatever the acceleration number is, every second, that's what I gain. So by taking the number of time seconds multiplied by the acceleration that's happening, this is the total velocity that I've picked up. So then I can say with confidence that the final velocity, whatever I end up, is going to be whatever the initial velocity I was traveling at plus the speed I picked up due to the acceleration. This much is the velocity I've gained. That's what this term is actually equal to. So if you go down here and write it again, v is equal to v naught plus a times t, and look at the units, it makes a lot more sense now that you know what the equation means, because this is the final velocity in meters per second. And this is the initial velocity in meters per second. These are just the same units, right? My final is going to be my initial. Let's just stop for a second and say, what happens if there's no acceleration? What if the acceleration is 0 and there is no acceleration at all? That means no speeding up and no slowing down. Then a is 0. Then there's nothing else here, and the final velocity is equal to the initial velocity, and that's it because there's no acceleration. But in the case of there being an acceleration, we have to add this, and this acceleration term is meters per second squared in terms of the units, and we're multiplying by seconds, right? So let me rewrite this again, meters per second. Instead of writing it as meters per second squared, I encourage you to think of it as meters per second per second. This is how much speed you're picking up every second, and you're multiplying by the number of seconds that's happening. So you can see that when you multiply a times t, the seconds on the bottom cancel, or you can think of it as one of these canceling here. And what you're left with is meters per second, that's a final velocity, meters per second, an initial velocity, plus the unit left over here is meters per second, which is the amount of speed picked up due to the acceleration. Graphically, it's the same thing. Final velocity is equal to the initial velocity plus however much I picked up over here, all right? So I could write it down, but this is final velocity, initial velocity, and then plus the amount of velocity I picked up due to the accelerating circumstance. If I don't have any acceleration, then I don't pick up any additional speed, and so then everything's equal. I'm doing this motivation through the idea of units because I want you to start thinking about units early on in physics. I ignored units a lot of times early and just assumed it would work out, but you got to have the correct units. And so if you're calculating a velocity, then whatever you're doing over here must give you a unit of velocity, meters per second. And this is how it happens, and graphically this is why it happens the way it does. Now this equation, which is one of the fundamental ones, I think is very easy to understand. Final velocity, initial velocity, plus whatever speed you picked up due to the acceleration over some time period, okay? This one is what I want to go over next, and this one is a little harder to choke down, so a little harder to understand why we have all these terms. But we're going to do it, so let's go over to the next board over here. So we want to do the same exercise. We want to understand all the terms by instead of just using it, we want to know why is it 1/2 at squared? Why is t squared? Why does this one not have a square? All these questions. So what we want to do is recognize that we have the same kind of thing going on. All right, I'm going to draw the exact same graph that I just talked about. We have some acceleration happening. I'm going to draw a little velocity curve here. We're starting out at some initial velocity. You can see it here. We end up at some final velocity here. And because it's constant acceleration, we move up in a uniform way towards our final velocity situation. And this is happening at over some time period t. And then we just said, just a minute ago in the last little bit here, that the amount of velocity we picked up is equal to the acceleration times the time. And then if you want to look at the units there, you can think of meters per second squared times second, and then these cancel, and so you get meters per second. So this is indeed the amount of velocity we picked up. So I just rewrite the whole thing I get. This is the speed that I've gained due to the accelerating nature. So what this equation means, when you see x minus x naught, remember x naught is the initial position. Usually it's 0 because you start at 0 on the axis. But if you start your motion at 5 meters and you end up 10 meters away, then 10 minus 5 is 5, and that's the delta x, the difference or the change in position that you have. So anytime you see x minus x naught written in an equation, in your mind think, oh, that's delta x. That's how far I've moved beyond my initial position. How far I've moved beyond my initial position. But usually x naught is 0, but that's why we have it there in case x naught isn't 0. If I start my motion somewhere else, I can still use the equations, okay? But this quantity, x minus x naught, this is the distance I travel. All right, so if this is the distance traveled, what is this? What is this? This is going to be, and I'm going to show you how in just a second, this is going to be the distance due only to initial velocity. If you think about meters per second times seconds, this is a distance number that's picked up just because of the initial velocity of the baseball or whatever it is. So if it starts out at the time zero of being at 2 meters per second and then accelerates, well, there's the initial velocity and then there's the speed that you picked up. So this is the distance traveled only due to the initial speed that you had. That's part of the distance you travel, but the other part of the distance is this thing. This thing I'm going to show you in just a second. This is the distance due to speed increase. Right? I haven't showed you yet, but this is what this is going to be. So what this equation means is the total distance traveled by a particle is equal to the distance that it's traveled because of the initial velocity the particle had, plus any distance that you pick up because the speed of the particle increased during the time window the acceleration happens. Okay? That's what this means. And if there's no acceleration at all, then a goes to 0, this term drops away, and then the total distance traveled is just equal to the distance you get because you're initially traveling with some speed. So let's just take a hypothetical experiment. Let's say we have a particle with no initial velocity and no acceleration at all. What happens? Acceleration goes to 0, this term drops away, initial velocity goes to 0, this term drops away, and the particle doesn't go anywhere because all this stuff is going to be equal to 0. All right, so let's rewrite this guy and put the terms in place. X minus x naught is equal to v naught t plus, I don't like that t, plus 1/2 times a times t squared. All right, now we've already kind of mentioned what this one is. This one is meters per second times seconds, right? So that makes sense. The seconds cancel and you get a unit of meters back. This is the one that gives everybody trouble, including me. All right, so what you have here is the way I want you to write this or think about it. Instead of thinking about it as 1/2 at squared, I want you to think about it as the following. I want you to think about it as acceleration times time over 2 multiplied by t. First of all, make sure you agree that this is the same as this. T times t is t squared, and then you have times the a, and then you're dividing by 2, which is the same as multiplying by 1/2. All right, so we've established this is the same thing as this. So then what is this thing? What is this thing right here? At over 2. At comes in our drawing. That is the speed picked up, right? So what we want to do is we want to figure out how far did I travel due to the increase in speed. But you see, during the time window I care about, initially I'm traveling at the initial velocity, and then I'm traveling at the final velocity. So if I want to figure out how far I traveled due to the increase of speed, what number do I pick? Do I pick this number, or this one, or this one, or this one? Because during the window of interest, the speed is increasing. How do I find out how far I moved due to the increase of speed when the speed is always changing? What you do is you say, well, this is just a line. So what you do is you say, well, I'm going to take the average velocity in this window. The average velocity is going to be halfway between here and here. Because remember, we're not considering the distance traveled due to the initial speed. That's taken care of over here. This is the speed increase only due to the increase, this amount. So this is the speed I've gained, AT. AT divided by 2 is going to put you right here. So this right here, this is AT over 2. This is the midpoint of the speed increase. This is the average velocity increase, in other words. I actually increased 10 meters per second, but of course, halfway through the motion, I didn't increase at all. And then eventually I increased all the way to the end up to 10 meters per second. If I want to figure out the average increase over the whole window, it's going to be half of this, AT over 2 right here. And then I use that velocity, AT over 2 is a velocity, the average of the increase in speed, and then I multiply by the number of seconds. And this gives me the speed or the distance that I've traveled due to the increase in speed only. So if we think about units, this is going to be meters, This we already said is equal to meters because of the cancellation going on. Over here, 1/2 AT squared, what you're going to have is this acceleration is meters per second squared, and you're multiplying by t squared. So what you get there, that's seconds squared. And then, of course, the seconds cancel with the seconds. Both of them do. And so what you end up with is meters equals meters plus meters. And so that makes sense because what you're trying to calculate is how far downrange has the object gone, and you get two things that you add together, both of which have units of meters, and that's going to be the total distance traveled. So that, in a nutshell, is why this equation works the way it does. It consists of two parts. I'm going to go through it one last time, and then that's going to be it. Here we have an initial velocity and some time elapsed, and then we have the acceleration happening over some time. So the total distance traveled is equal to the distance due to the initial velocity, however fast I'm going, times the whole time window. That takes care of the distance I cover only because of the initial speed that I have. But then I gain additional speed. I gain additional speed all the way to some final velocity here. And if I want to figure out how far I traveled due to that, what I do is I know that I started someplace and I ended someplace. I just take the average of the two to find the average. Because if this is the average, half the time I'm traveling slower than that, and half the other time I'm traveling faster than that. So the average is exactly in the middle, and that's the number I use to find the distance traveled, because half the time I'm going faster and half the time, or slower, and half the time I'm going faster. So AT is the velocity I've gained. AT divided by 2 is basically the average of the velocity I've gained, or halfway to the endpoint of the velocity I've gained. So then I take that average velocity increase, multiply it by the time, and that's the distance traveled due to the increase of speed. So I have the distance traveled due to the initial velocity, the distance traveled because I've increased my speed, and of course the units work out meters, giving meters as an answer. You know, most people, when they study physics the first time, including me, you learn these equations, and honestly, you just assume they're true, and you just use them. And half of the battle is learning to use them. And I'm going to teach you how to use them. We're going to do a lot of problems that really show you how to use these equations, because there's some skill to it, okay? But I don't want to shortchange you. I don't want you to think that equations just fall out of the sky. And, oh, they just fall out of the sky. And so here it is, use it. I want you to understand where they come from. I mean, maybe not for every single equation, but for at least the ones where we can gain some real understanding of what we're doing here. Because if you understand what you're doing, then it doesn't seem like a bunch of magic. You're logically figuring things out. If you don't know what the equations are, and you just say, well, I'm just literally going to try to find one that I can solve for this, and that's it. Eventually you'll reach an upper limit to your understanding because you don't really know anything beyond a superficial understanding of it. So in this lesson was all motivation. We wrote down the equations of motion. I told you that there's two core fundamental ones, and these three come from those. We said that each one of these equations has a quantity missing, which means sometimes we'll use one equation preferably over another one. And then we did a motivation with units to show you that the core equations make sense. And then we also actually took the derivative of these core equations to show that they also make sense. So by now you should believe me. You should say, okay, they make sense. I still haven't seen the proof, but they seem to make sense. Now what we need to do is go to the next lesson, where we're going to derive not one, not two, but all 5 of these equations. You'll probably never use it again. Maybe it'll be asked on an exam, but in the back of your mind at the end of the next lesson, you will know where they all come from, and it will be very easy to understand. So make sure and go through this a couple times so you understand what these equations are. Follow me on to the next lesson. We're going to derive the equations of motion with constant acceleration.